continuing on with part 4 of class 3 in ME470 and dealing with gears in chapter 13, and we're going to talk about these fundamental relationships between gears, gear pairs. And I think of these as having 4 things that have to be true about a gear pair. First, they have to have the same pitch. They have to have the same pitch line velocity. They have to have equal and opposite forces, and the power in has to equal power out, right? So these 4 things will establish what the gear ratio really means. Now, I'm going to use 1 is going to mean, I think I'm going to say that it is going to be the pinion. I have it written down wrong over here, just so you know. And number 2 here is going to be the gear. Okay, so if we hit for a pinion, we have to have the same pitch as the gear, right? So if we find the pitch, we could find the pitch by taking the number of teeth and dividing it by the pitch circle diameter. So if it's true for the pinion, it has to be true for the gear, right? So, and you can see what these relationships are going to be if we were to take the number of gear teeth and divide it by the number of pinion teeth, and you'll notice that this one has more teeth than this, right? So this is going to have a higher speed than this. By the way, we'll see that in a second. We have this ratio right here. Well, then the diameters too are going to have that same ratio, and we could call it this, the AKA, that's M subscript G, call that the gear ratio. Now, Shigley doesn't use this quite as much as maybe other books or in the discussion right there. It does come up in there. I double checked right here. Here's where gear ratio, it's only brought up in the discussion of interference is where they call the gear ratio. You can also see later on. Now this says for bevel gears, but they define that M subscript G as being NG, number of gear teeth divided by number of pinion teeth, right there. So and also sometimes they'll use lowercase m right there, right? So in this equation, so you have to be kind of careful. They remember from the previous video, they used lowercase m for module, which is something totally different. So watch out for these variables. They can really trip you up. Other places, I think, like right in here inside this example right here, they have a gear. They describe the gear ratio right in there. So anyway, back to this right here. Now they have to have the same velocity, right? Well, this tooth can't pass through that tooth, so they have to share the same velocity. So the pitch line velocity is going to be the RPM, or here I'm going to use this is radians per second, times the radius right here. That's going to be the definition of the speed at a point on the tooth is just going to be that times the radius, right? So that's the diameter times the time. And it also turns out to be along the pitch line, it's going to be times the cosine of phi right there, right? So this is really the base circle radius right here times this, and that's going to be for the pinion. It has to be equal to the same thing as the gear. But you could see, so that's how you get the linear velocity along the line of action. We have another equation, the go-to equation, that we can use for this as well. So just be aware that we won't use this equation quite as much as that other equation. In fact, let me pause a second and then find that in the book and make sure that you're familiar with it. Most often will be given by this right here, right? And it ends up being in feet per minute. So when we define pitch line velocity, I just want to be clear that the previous equation that I used, while it is true, and you'll see right there, that omega times the radius right there, that we kind of define it as a formal thing. So be aware that's equation 1334, at least in the 10th edition of there. All right. So, but I have defined it right here. This is just as valid with this. But the point on this one is these ratios, right? So if we were to take omega 1 divided by omega 2, now this is the speed ratio. That's an important trait, right, of the input speed versus the output speed, something we want to know. We could also see that that's related to the diameters right here. So that's going to be, and there's an inverse relationship, right? So a faster one has a smaller diameter. And if you look up above, that's 2 to 1 right here. So that must be equal to 2 to 1 here, right? So there's the diameter ratio. We have it down there, so that must be equal to this. So that's also going to be equal to this gear ratio mg. Now we also take a look, the forces have to be equal and opposite, right? If this one is pushing on that one, this one's pushing back against it, right? So that one is that way, that was that way. So in order to do this right here, we're going to take the torque, right, and divide it by the torque arm, which we happen to know is going to be the base circle radius right there, or cosine times phi. Right, and this is going to be for 1, because this is for the pinion. Well, it better be the same thing here, true for the gear. So take the torque, what's supposed to be 2, and divide it by the base circle radius. So now if you take, some of these things cancel out right here, so we're going to say a torque ratio is going to be now directly proportional to the diameter ratio, which, remember, like here's the diameter ratio, here's the number of teeth ratio, so that too, right? And you can see that these are opposite, right? The torque and the RPM are inverse to each other. So as a speed is reduced, the torque goes up, right? So this is going to be moving faster than this because of the diameter ratio right here, right? This one has more teeth, this one has more speed. And then we could also confirm that with conservation of energy and conservation of power here, or the rate of energy, right? So as a, and let's put these in simple terms right here. If we just have torque times RPM gives us power. Therefore, torque times RPM also gives us power. So you see you have the inverse relationship where we have, arranging these, so you have the speed ratio right here, right? Yeah, and I think that's correct. Yeah, so now you're going to have the output torque divided by the input torque right here, and so we have 2 to 1 here, 2 to 1, and that's going to be the gear ratio right there. So it reduces speed and it increases torque when from this pinion to this gear right there. So you have there you go. There's the fundamental relationships between gears. And the best thing to do is to work through and find what I think to be able to keep these straight about what the cause and effect of having a number of teeth to each other, right? So more teeth to lesser teeth right there is going to reduce the speed, right? So we're going to end up having a speed reducer, and it's going to increase the torque. So high speed, few teeth, lower speed, more teeth, less torque, more torque. Okay, so I guess I'm gonna continue with this. Other traits that are important to us, one is the contact ratio, right? So this is a function of many things. I went ahead and used an equation, found an equation from another textbook. Shigley gives us sort of this kind of foundational approach to describing the contact ratio, but then doesn't really give us an easy to use equation to be able to get it. And then interestingly enough, unfortunately, we use another lowercase m with another subscript here, in this case C, for contact ratio right here. And it's a function of many things in here, but you'll see that pressure angle is one of them. Pitch is also involved because we have the diameters, right? Number of teeth are also involved. So it has a function of all those things, right? The number of teeth, the pitch that we choose, and the pressure angle. And so as Shigley is describing it, they figure out this geometry of this length right here, and then they take a ratio to find it. In my research, what I used for modeling of gear vibration was this periodic change in stiffness that occurs because of the number of teeth engaged at any time, and that's what contact ratio is. You can think of it as the average number of teeth pairs engaged at any time, right here, or through a cycle of changing up. So as you're right now in this situation, there's only 2 pairs of teeth, right? But as the thing's rolling over, there initiates contact. While this is still in contact is initiated right here. And so for a brief amount of time, there are 2 pairs of teeth engaged. And then as this continues to roll, this disengages. So when there's more pairs in contact with each other, the stiffness will increase, right? But when it lets go and now there's only 1 pair of teeth engaged, the stiffness reduces. And that is in essence the fundamental thing that's causing vibration in gears, is that it's stiff, less stiff, more stiff, less stiff, more stiff, less stiff. And that's going to, in effect, cause some of that non-conjugate action, some of that thing we call transmission error, where it isn't a perfect rotation to rotation transference right there. And so that's the idea behind contact ratio. And so you'll see stuff like a contact ratio probably doesn't want to go below about 1.5 or 1.6, I believe, is like kind of like the typical range right here. But if you want to say the average number of teeth in contact is really kind of the idea. It's not exactly. So you can think of this as like a mesh period right here. Is a periodic thing, like from here to here is one period of engagement where we have, right there is where the period starts, right, according to this thing, because there are 2 pairs engaged, and it lasts for some of, and then it goes away, right, and then so like we could actually start like right there with these these teeth right there. So this one is driving this one in this case. We move that right down there. We can see that engages, and let's go, and then this starts to happen. Move on to there, right? So it's the motion, the transference of load from one to another. That's what contact ratio is. Now, similarly important here is interference. And interference occurs when this tooth right here kind of like presses up onto the mating gear, like down here in the root right here, right? So or the same thing, this guy right here. So interference can be thought of as a consequence of the number of teeth engaged, right? So there's always some portion of the tooth that's not exactly an involute, and that causes interference. It's also just part of the nature of trying to manufacture the gears. They're not going to be a perfect involute as part of the machining process. So there's a chance to have some interference. It's something we want to avoid. Also, the smaller number of teeth that we have will cause interference. So there's like a minimum number that we can have that would not cause interference. I do include the thing I mentioned in I think in one of the other videos, something called backlash. You can think of that as the amount of play that you have. Like I hold this stationary, and we can come back and forth, right? And backlash can be a good thing because it avoids some of the interference. We could avoid some interference by moving these away from each other, right? Ever so slightly. But then the contact ratio gets affected by that. We can actually reduce the contact ratio by artificially moving these centers away, right? The correct center to center distance is the average of the pitch circles, right? The pitch diameters. But we can have, but if we artificially move these away, we change contact ratio. We do avoid interference right there. We can create interference by making these things closer to each other. So there's a number of equations right here to be able to calculate what the minimum number of teeth is, right? So it's kind of a little confusing because they have multiple equations with for things. This first one is just when you have, like, if you just had a 1-to-1 gear ratio, and now you're not changing speeds or torques or anything. A lot of times you're just doing that to change direction of the shafts, or just the orientation. You want to keep them. You want, for whatever physical reason, we need to have the shafts offset from each other. We might have a 1-to-1 ratio right here, but we could find what the minimum number can be, and you could see that it's a function of pressure angle more than anything else. We got to double check what this K is. Let me pause and take a look at what that K is as a refresher. Okay, so here is K, my refresher is K is equal to 1 for full depth teeth, but it's 0.8 for stub teeth. Now that's something that we might do to the teeth themselves on purpose. We might cut them down and make them on a lathe and make them short. So we're actually reducing the dedendum when we make these stub teeth. It's a way to reduce interference. So that's what. So K is equal to 1 for typical things right here. So you can see it's really when it's just 1-to-1, it is a function of pressure angle. Is the only thing that really makes that decision. Now, if you have mating gears with more teeth than the pinion, which is typical right there, the smallest number of teeth on the pinion without interference is going to be this right here, right? Once again, that K is for stub teeth. You'll see this M is in there. They mean M is same thing as this gear ratio that we just defined previously right here. So you can see that it is a function of that gear ratio. And then we could also say that the largest gear with the specified number of pinion teeth for interference free is going to be based on here, and so it's going to be based on the number of pinion teeth in there and the pressure angle, right? So what we find when we go ahead and use a standard 20-degree pressure angle, we will find the minimum number of teeth is going to be 13 right there, right? So if we're coming back up into here and we use 20 degrees and we use for a gear ratio placed into this, we end. Let's see, did I say that the right way? Okay, so I just put into this 13 into there. Yeah, we end up getting 16.45 gear, and so we get an integer of 16. which is a gear ratio of 1.23. If we say do the same thing for the pinion teeth for a 14, you can see that we start to come up here. Above 17, we're fine right here. Something we got to be careful with, though, when we go to this is anything above 17 starts getting us something really weird up here. We might start getting a negative number. So this equation is really only good for a short range of problems, right? So you just want to be aware of that. That this is not like this universal magical equation that will work above a certain level. You'll end up getting weird results. But anyway, let's see. Continue on a little bit more, even though it's a long video. Some other things that we want to know about the forming of teeth and the way that they're formed. Let's take a look. Okay, I didn't include this with my contact ratio. All right. Oh, and here's an example of interference. I wanted to point this one out. Let's see here. Let's see if it'll come up. No, didn't work. Huh, I thought this was gonna come up. But we can have interference by way of, we could demonstrate interference. Let me demonstrate interference here. All right, well, this class is running a little longer than, or this video is running longer than I meant to. Here is an example of some interference. I didn't quite get this the way I wanted to here, but you can kind of see where we have some impingement taking place, like right there. We're using a very small number of teeth in order to try to demonstrate this. For the I messed around with a couple other things to try to demonstrate some of the interference possibilities in there. It's running through the numbers will give you some odd results in the number of gear teeth, so be aware there. But this is a really cool tool to be able to just mess around with the different gears combinations of things, where you can see that I can highlight this particular gear here, or I could actually start clear and remove. So this is from scratch right here. You can see that we have the number of teeth is 10 right here, so we could increase the number of teeth of this first gear. You could change what the pitch is going to be, like I can make it like here's 6. I think I'm at 100% display. I can increase that display, but like there's 11 teeth with a pitch of 6 right there. Some of the examples for the thing, let's say we had 13 teeth, right, where they were saying that was the minimum number for non-interference. And I have a pressure angle of 20. You can increase the pressure angle, but 20 is like standards. Like it doesn't come in a whole lot of other pressures. I think like 20 and 21 and 22, and then 14.5. I don't know if there's that many others. They'd have to custom make them. Now, so if I was going to add another gear, I could add a new one right there, and we want to maybe zoom in on this, and if we can. We could also move. I think we can move where they're located right there. We could change the angle at which they're located right there. We can move that thing around so we can kind of like get in the center. And then I'm going to change this to 1 RPM and start the thing up so we kind of see. I mean, there's not supposed to be interference, but we can look for it as in here, and yeah, you can kind of see. So like what would happen if we were to say instead change these to something smaller, change this to something smaller as well. Whoops, I want to click on this guy. It's not letting me. There you go. There you go. So let me change it to 10 on each of these. Let's see, there's 10 and 10. And let's see if we can see any interference. Don't see. See, you would see some of the tips impinging on the sides, like right in there. But that's backside. But you could kind of, yeah, we're looking for some of that interference. But anyway, that's the big idea with interference, is that they could possibly interfere here. So here's where you can see some of the undercutting that could take place right in there. Now, undercutting can solve interference, but undercutting can also be the consequence of the way the hob is coming through here. And as I wrote here, the gears aren't perfect, so adjustments have to be made. And there's other ways that we can make adjustments called profile modifications. And one of them is to doing tip relief, which now, because it's the tip that could impinge into the flank right here, we can knock off a little bit of the tip right in there. That's going to change also the contact ratio, the amount of time that the thing is engaged, but it can solve some interference problems. Other things that we might want to do, and this is not necessarily for interference, at least not interference in a standard setup, but we also might want to crown the gears, which is like rounding off some of these right here. And then there's also end relief, right? So crowning is actually more like rounding the whole thing, rounding this whole thing out. And what that helps with is if there's misalignment this way, right there, right? If the shafts are misaligned, or even if they deflect so much, now if they're hitting in the side, right here, there's a more amount of tolerance to be able to have like a twisted off where they're now they can kind of roll. But of course you're taking away material from the strength of the thing in any of these cases in the modifications. And I think the last part here before an example is I just want to point out the other systems of teeth that are possible. So this comes out of Mark's standard handbook for mechanical engineers. And I'll note that there's differences here. So there's other types of teeth setup here. So you can see 14 and a half, 20, 20. Oh, there's 25 right in there. Okay, so there's some. You can also see things with the addendum. Like, see, here's for stub teeth. Here's the 0.8. So you can see those are different. You can see the dedendum right there. So we said it was 1.25. Which seems to be like right there. That's true, and that's true. That's for the dedendum, but you can see that there's other things besides here. And then here's from a catalog right here from Boston catalog. I thought this was a nice collection of various things that you might want to calculate for here. So yeah, and here's contact ratio. So here's another equation for contact ratio. So this video went way too long. I'm not sure how many people are going to benefit from it. It's almost half an hour long. So if you added up all of the videos, that makes for a very long class. So I'm going to try to be more efficient. I'll post the videos just in case it could be helpful to someone. Thank you.